So I'm going to talk to you today about this indoor chemistry work that we did, thinking about the chemistry of a home, and it's particularly relevant. I think almost everyone is sitting at home. And so what I want to do today is to get you to think a little bit about what you're seeing and in your house and the chemistry that's going to happen there. So overall, I'm going to talk to you about the HOMEChem project funded by the Alfred P. Sloan Foundation. And it really gave us the opportunity to think about the extent to which the air that we breathe and the chemistry in our homes is influenced by our activities and the products that we choose. And in particular, probably much to the shock of my husband, who's forced to listen to the seminar on the other side of the room, I'm going to talk to you about cleaning and the chemistry of cleaning products. And that's really because the chemistry is quite fascinating. So I'm going to show you some data that was collected by a very large number of students and postdocs from a huge number of institutions around the United States. And in particular, I want to call out the person who made this beautiful graphic that you see, my co-PI, Nina Vance at the University of Colorado in Boulder. As well as the huge number of researchers from the University of Texas at Austin, led by Dr. Attila Novoselak, who ran a house, which turns out to be a very complicated instrument in itself. And then I'll talk about some of the other measurements that we made. So we spend 90% of our time indoors, and that was pre-pandemic. And that's impressive because most of the air quality and health research that we've done as a community has been focused on outdoor air pollution. Traditionally, we've correlated health outcomes to outdoor particulate matter and ozone. And this raises a really substantial question, right? If we spend so much of our time indoors, why is it that our outcomes correlate to outdoor air pollution? So I want to raise a couple of questions. First, what controls indoor air chemistry and how similar is it to outdoor air? So we can think about the sources, and you can look around whatever room you're sitting in, and there will probably be electronics, painted walls, maybe you can see your kitchen. Those are all very interesting and different sources of volatile organic compounds and inorganic compounds. We work on very different timescales in the indoor environment from the outdoor atmosphere. So we really think about reactions. They only have minutes to operate on the indoor environment if you're looking at fast chemistry. On the flip side, though, surfaces stay indoors for decades, potentially. So you're looking at really different timescales inside. If you look around your room, the surface area to volume ratio is quite large. And you will find this obviously puts us in a very different scenario from what we would see outdoors, where surface area is really limited to thinking about particle surface area. But here we have much more complex surfaces inside. And then finally, even if you have all the lights on, the light and photolysis rates inside of a building are very low. And so we're in a very different photochemical regime indoors from where we are outdoors. So we can really start to think about what's different between indoor and outdoor air chemistry, what controls that chemistry, and then we can think about the fate of any molecules, trace gases, or particles that are in our indoor air, and to what extent they start to influence outdoor air pollution. So what's the fate of indoor air? Of course, now we're in a really interesting scenario where I think all of us here are spending up to 100% of our time indoors. And it's obviously essential and far healthier to be indoors than to go outdoors and mingle with other people. But I think this has put us into a new position in terms of thinking about our indoor air and how we are influencing this chemistry. So I was originally going to give this seminar on a totally different topic, but because of the current situation, I thought it would be a little more interesting to talk about indoor chemistry. So the study that we ran was HOMEChem. And HOMEChem was the House Observations of Microbial and Environmental Chemistry study. So what we did is we took over 30 state-of-the-art instruments from 13 universities, plus instruments from industry and government collaborators. And we ran them for 4 weeks in June of 2018. We did this at the house, and you can see this photograph right here, the U Test House at the University of Texas at Austin. This house is a very standard prefab 3-bedroom, 2-bathroom house. It's actually representative of a very large amount of the housing stock in the United States. Nothing fancy about it. But the goal was to really characterize aerosol and gas phase chemistry during cooking, cleaning, and occupancy. So we wanted to understand how activities changed that indoor chemistry. So this was a bit like an inverted atmospheric chemistry experiment. So we did take all of our instruments and we put them in trailers, and you can see this picture of some of those trailers decorating the outside of the house. And then we took inlets and we ran them inside into the kitchen and into the living room. And so we could actually just measure the indoor air. We also had inlets reaching outdoors, so we could think about the difference between indoor and outdoor chemistry. So here's a picture that was taken of looking indoors in through the window during one of the occupancy experiments. And I love this picture because it tells you exactly what should be happening on a field campaign, which is that all the instruments are running and we have all the graduate students sitting there working on the data on their laptops. And so this was the epitome of HOMEChem, right? You want to actually see what human emissions are. So you put humans into a room, and then you can see the inside of the house is decorated with instruments. So right in front of the window, you see the top of Phil Stevens's OH instrument. And then you see a little spectral radiometer from Tara Kahan's group. And in the back, you maybe can make out a Picaro ammonia instrument, a huge array of aerosol measurements. And then on all of the walls and ceilings, we had temperature measurements. And those are really important because they give us our boundary conditions for effectively, you can think of it as parallel to the meteorology inside a house. But we wanted to understand the airflow because that, of course, is essential to understanding chemistry. So we had a huge and wonderful group of researchers. So you can see here the picture. This was taken on an open house day, about 2/3 of the way into the experiment. And you see just this lovely array of students, postdocs, and PIs from a huge number of institutions. And so what we did throughout this month was what we broke down into 2 types of experiments. The first was a sequential experiment. And that you can think of as the idea was a very simple but replicated activity. So we did things like mopping the floor. And so we would mop the floor, and then whoever mopped it would leave the house, and we would just wait for a couple of hours and watch the chemistry. And then we would go in and open all of the windows, ventilate the house, clear the air out, close them all up, wait a little bit longer, and then go in and repeat the experiment. So mop again. The replication turned out to be quite tricky because something as simple as mopping the floor is hard to replicate. So you can have a graduate student who is a little more enthusiastic, say, than other, and goes in and mops the floor very vigorously. Well, it turns out that in that process, the student will then release a shed, a whole number of coarse particles, supermicron particles, because through their activity, and that's skin cells and fabric and little pieces. And then you, of course, would release a different amount of mopping material. So it took us a while to figure out how to standardize these experiments. So very specific amounts of time, space, and then having the same person do the same activity over and over. So those are what we called sequential activities, so single activities separated by time. Then we wanted to ask what happens, do these activities interact with each other? Does the chemistry of my Bleach mop interact with the chemistry that's being emitted when I cook a stir fry? And so in order to think about that question, we did what we called a layered experiment, where we just layered multiple activities on top of each other, simulating what one would do in a regular day in house. So we would cook breakfast, wait, mop the floor, cook lunch, wait, cook dinner, run the dishwasher, mop the floor again. So it was a very, very clean house. But the idea was to, instead of ventilating the house, we would look for all of the interactions between the different molecules. And this turned out to be really important. It really matters what you did a few hours ago in your house. That really changes the chemistry. So this allowed us to ask some interesting questions. Cleaning, of course, adds solvents. It adds surfactants. Depending on what you use, you may be adding acids or you may be adding bases. So you're changing the chemistry. And you can ask, to what extent does the chlorine, say in bleach, interact with the nitrogen and the organic carbon indoors? What oxidants influence the indoor chemistry? And to what extent does this chemistry impact aerosol production? So we can use these experiments to ask questions that are really interesting that we've been thinking about perhaps from an outdoor perspective. So this led to a pretty rigorous cooking and cleaning schedule, as you will see here. This is our month of June in 2018. And so what we had was a huge array of these sequential, so separated experiments, and then we had these layered experiments, and then we did a few highlights, including cooking Thanksgiving dinner a few times, which if we have time, I'll get to at the end of this presentation. So just to give you an example of what the data looked like, and this was really fascinating as an outdoor atmospheric chemist because, of course, the concentrations looked so very different. So what you see here is a day from midnight to midnight, local time on the x-axis. And then each of these subplots, you can see different concentrations. And so CO2 down on the bottom, you can see, of course, as we added more people, the concentration rises. And then whenever you cook with a gas stove, the concentration of CO2 can go up. So we got on average some pretty decently high concentrations of CO2. So 1,000 or 1,500 ppm when you were cooking was not abnormal. Ozone was really interesting because it turns out that all the surfaces of the house, of course, also the surfaces of any humans inside the house, all react with ozone very, very rapidly. So ozone concentrations indoors were very low. This was also coupled to the fact that we had pilot lights on the gas stove. So we actually had a fair amount of NOx just in the background of the house. And so our ozone rarely went over 5 ppb unless we opened the windows. You'll see an excursion in that here, and that's, we think it's actually an instrument interference potentially from when we bleach mop. We're still working on tracking that one down. NOx was very high relative to outdoor air. So when you cook, it could be a couple hundred ppb. Then your hydrocarbons also are quite interesting. So it turns out that humans emit isoprene when we breathe. Of course, when you cook, if you cut up a lime, you'll emit limonene, or if you clean with a pine sol-like terpene based cleaner, you'll get very high limonene levels. And then, of course, if you cook and your water is treated, is disinfected using a chlorine-based process in your municipal water system, you'll get a bit of chloroform whenever you cook. But obviously, when you bleach mop, you'll get a very large emission of that. So overall, what you can see in this picture are that most trace gases are very high relative to outdoors. The major exception is ozone, and under most conditions, OH and HO2 radicals. But what's interesting as an outdoor atmospheric chemist to me was that activities could change the concentrations very, very rapidly and across a very large dynamic range, right? You span hundreds of ppb in a matter of just a couple of minutes. And what was really exciting about this project was that we had some really fast time response instruments, and those really hadn't been used widely in the indoor chemistry community. So this really just illustrates the role of different sources, as well as the role of indoor-outdoor exchange and different activities and different products. So what I want to do now is run through some questions of what the indoor versus outdoor pollutants look like. Then I'm going to tell you a little bit about bleach chemistry and equilibria because it's fascinating. And then if we have time, I'll tell you a little bit about instrument interferences and what happens when you cook Thanksgiving dinner. So how does the indoor air contrast to the outdoor atmosphere? Older houses in particular are relatively porous, and so you get a fair amount of exchange of air. And so the way I started looking at this data was to think about this in terms of histograms. And histograms will tell you about the average state. And of course, a lot of the time during HOMEChem, we were just not doing anything because it was night. There were no activities being done. And then we would get these occasional perturbations. And so what you're seeing here is each trace gas has its own little subplot. And you see the histogram. Indoor data is red, outdoor data is blue. So if we start on the top left, you see this ozone data, and you can see that outdoor ozone was pretty normal for a city. It got up to, I think our peak was somewhere around 60 to 80 parts per billion at the end of June for Austin, Texas. That was a very short period of time. Most of the time it was sort of 50 ppb. So relatively clean for a city in Texas. But then you look at the indoor ozone and you see that the ozone concentrations are substantially lower. And really you're looking at about 5 parts per billion of ozone, if not less, depending on how you trust the instrument backgrounds. CO, so carbon monoxide, we get a little bit of an inversion in that because, of course, combustion and that pilot light are going to continuously produce some of that carbon monoxide. So that's always higher than outdoors. And then the other interesting components are, of course, NOx. And again, that pilot light gives us a continuous source of certainly of NO, and then a little bit of NO2 that's higher than the outdoor average. So ozone is consistently low indoors, and that's really important if you're thinking about chemistry. All right, so then what about light? So this is some data from Tara Kahan's group. And what you can see is that indoor light levels are very, very low. So these are the Che values for the photolysis rates for HONO, as determined from both an east-facing window and a west-facing window. And of course, because the roof blocks the sunlight in the middle of the day, you get some really funny patterns. And the spatial patterns within a home are incredibly complex. And they operate both in the vertical and of course in the horizontal axes. So it turns out to be a really complicated problem to figure out an average photolysis rate. But no matter what, if you take, these are measurements taken at your peak, the highest possible photon flux that you could measure, you get those next to the windows. And no matter what, they are a lot higher than the outdoor photolysis rates that we're used to seeing. There's obviously negligible ozone photochemistry, photochemical production of ozone, and there's just very little light for photochemistry. And of course, there's no dual pattern. Indoor particle concentrations tend to actually be a lot lower. And this is really important because the media loves to tell you that your particle exposure indoors is, as bad as a bad day in Delhi and India pre-pandemic, but that's not quite true. Your indoor particle concentrations are generally, if you're not doing any activities, are influenced only by air pollution coming in from outdoors. And so the PM, the particulate matter concentrations are quite low unless you are cooking. And when you cook, your particle distributions become quite fascinating. So you can see some data here, depending on what size range you're looking at. But if you look at total particulate matter up to PM20 in when we were just stir frying, we would get up to sort of 400 to 500 micrograms per meter cubed. It turns out that the density of this aerosol is an interesting question. It looks like it's mostly, if you're cooking with vegetable oil, it mostly looks like oleic acid, so about 1 gram per centimeter cubed. But of course, the size-dependent densities are a big question. And size dependence, it turns out that different when you cook with toast versus if you cook chili or you cook a lasagna, you're going to get very, very different size distributions of your particles. And I just wanted to note, again, so here's some of the time series of that data. So if you look at the bottom left slide, you see a time series that shows that your average indoor concentration, so those are in the blue colors, so the lower time traces on that left-hand plot, those are all about 100 particles per cc in the accumulation mode, as opposed to outdoors where they're about twice as large. But the size distributions tend to follow each other in background conditions. I thought it would be fun to think about, when we say cooking concentrations are high, to contrast it to the other field experiment that we did in the summer of 2018. So here you see data from a peak event, a stir-fry event during HOMEChem, and you can see this is aerosol mass spec data, and you can see that the peak concentration was around 50 micrograms per meter cubed, and it was dominantly, over 97% organic aerosol. And of course, we went straight from that to the We Can aircraft campaign about a month later. And there we were seeing, if you flew into really substantial smoke plumes, I think about the highest we saw was about 1,100 micrograms per meter cubed. So the emissions were high at HOMEChem, but they weren't smoke plume high. But they did create their whole own set of interferences and analytical challenges in terms of measurements. But these are both combustion sources, and they are both dominated by organic aerosol. All right, so one other set of compounds, then we obviously are interested in the volatile organics. So organic acids are interesting because they're water soluble. And of course, the HVAC system, which was running continuously, June, Austin, Texas, particularly at the end, it got to be pretty warm. And so what you see is some really interesting things. So the figure on the right, you'll see each subpanel gives you a different organic acid that we measured. Indoor concentrations are in green, and you will notice that they are on different axes from the outdoor concentrations that were measured simultaneously. So if you look at the very top panel, formic acid, one of my favorite carboxylic acids, you will see that the average concentration indoors was about 30 parts per billion. Outdoors, it was about 1.5 parts per billion on average, maybe 2. And so you also see some really large fluctuations indoors, and that fluctuation corresponds to the HVAC system. You are forcing that air to interact with the cooling coils. So you get some really interesting acid-base chemistry happening. It turns out the buildings, just the building itself, can actually be a pretty substantial source of some of these organic acids to the outdoor system. We estimated the house we were working with at least would be about 3 times the soil emission. And so that's really just the building material itself. Of course, certain events can produce really large concentrations of some of these acids. And then, of course, it's also important to note that not all acids behave the same way. It's very hard to find just blanket patterns that you can apply to everything in the indoor environment. Certainly, outdoor air was a source of glycolic acid to the indoors. So not every acid comes from the indoor materials, but a huge number of them do. So the last sort of interesting set of molecules to point to, I know we have several people on the call who actually measure these, are in terms of the volatile organic compounds, are monoterpenes. As you'll know, I spend a lot of time thinking about biosphere-atmosphere exchange and plant emissions, and I thought I had a pretty good handle on what monoterpene concentrations might actually be. And certainly when we weren't doing anything in the house, the background concentrations would be generally less than a part per billion. We would have about 0.2 part per billion of limonene and about 0.7 part per billion of alpha-pinene. And then when you clean, everything changes. And so you can see when you clean with pine sol, bottom left, you maybe get up to about 10 parts per billion of monoterpenes. When we cooked Thanksgiving dinner, it turns out that cutting lemons and limes are such a massive source of monoterpenes that we would actually get, I think our maximum limonene concentration was 116 parts per billion, relative to 16 parts per billion for alpha-pinene. So while indoor monoterpene concentrations, when you're not doing anything, might be similar to outdoor concentrations, as soon as you cook or you clean, you can get really, really high VOC levels. And this raises the interesting question, right? These are very reactive molecules. What kind of chemistry can they do, and can they export outdoors? So in terms of just thinking about how indoor air contrasts to the outdoor atmosphere, we can think about very high concentration of VOCs. We can think about very rapid changes in concentration, and we can think about very low loadings of oxidants. So this is a very, very different environment from the outdoor atmosphere. But that question about those really high monoterpenes was nagging at me all summer of 2018. So finally in the fall, I managed to, fall of 2018, I sat down and I looked at the data. And I said, okay, is there any evidence for organic aerosol production because of these, high additions of monoterpenes? And it was quite intriguing to me, but then it made sense that if you look at the organic aerosol before versus after you mop with something like pine sol, you can see technically there can be a substantial increase in concentration in organic aerosol, but it's not significant. There's very little evidence for SOA formation, even with very large additions of volatile organic compounds. And that's really because the ozone is so low indoors, right? 5 parts per billion relative to outdoors. And then your air exchange rate in the house is about 0.5 or 0.6 per hour. So you don't have very much time to do reaction to make aerosols. So you've got very low oxidant concentrations and not very much time to work with. So we don't see, in a bulk SOA sense, we don't see a huge amount of organic aerosol being formed indoors. But that doesn't mean there aren't other chemical transformations. So we spent a lot of time thinking about this cleaning chemistry. And again, I was starting to look at these monoterpenes. And so here's some examples of 3 different bleach cleaning events after we had cooked dinner. And you can see what happens to the alpha-pinene, isoprene in green and limonene in orange. As you can see that the concentrations, the moment we cleaned with bleach, and this was a GC measurement that was quite slow, but you would see that the concentration of all of those monoterpenes would just nosedive and get really, really low. And that told me that there has to be oxidation chemistry. This was much faster than we could possibly explain just through air exchange with the outdoor environment. So there was evidence for some chemistry. So my graduate student, Jimmy Madela, started to think about this chlorine chemistry and what could happen when bleach, when you mop, interacts with VOCs that are in the air. And it was kind of entertaining because on his PhD candidacy exam, one of the faculty committee members asked, well, does anybody even use bleach? Like, how common a problem is this in homes? And of course, now we're really realizing that chlorine bleach is widely used, particularly now. And in fact, this is some data that was put out by the CDC showing calls to US poison centers about cleaner and disinfectant exposures, and they've increased by 20% recently. So this chemistry is very, very relevant, and there are some fascinating case studies that the CDC has been finding that really highlight the importance of this chemistry. And one case that the CDC calls out was a woman who heard that it would be a good idea to clean groceries before you eat them, filled a sink with a mixture of 10% bleach, vinegar, and hot water, and soaked her groceries, and then noted a noxious smell described as chlorine gas in her kitchen, and obviously had difficulties breathing, called 911, turned out to be all okay. But this is a great example of the kind of chemistry that bleach can do inside homes. And so this is the sort of chemistry that we're going to think about, but not by purposeful mixing of vegetable matter with bleach, which is a terrible idea. And adding acids to that is even worse. Okay, so how we did this, my group's been using chemical ionization mass spectrometry for quite a while. So we took our instrument, we were using iodide reagent ions. John Abbott's group was actually running their sims using acetate reagent ions. So we have a pretty impressive suite of oxidized organics. So here's a picture of Jimmy Madela, my students, threading through the inlets that we were going to use to do all the measurements in the kitchen. And what he saw is really quite fascinating. So mopping with bleach, and we should make very clear that we made solutions according to manufacturer instructions, as one should, and used them according to directions. And so these were not particularly concentrated solutions. We just mop the floor. And these were sequential mopping events. So we didn't cook before them. There was no addition. So these evening events were about the 4th or 5th time the floors were mopped in a row. And yet there was still evidence for some pretty interesting chemistry. So in the top left, you see hypochlorous acid. So the key ingredient of chlorine bleach is sodium hypochlorite, which forms hypochlorous acid. So we would see that rise very rapidly. And then we would see, and those concentrations would get up to a couple of 100 parts per million. We would see Cl2, so chlorine gas, molecular chlorine, would actually get up to about 60 or 80 ppb immediately after the mopping was started. And then we would see an array of other compounds, including nitrile chloride, so ClNO2, and then of course chloroform and other compounds. So bleach was a source of halocarbons and inorganic chlorinated compounds. But we weren't just interested in these initial emissions. We wanted to look at the secondary chemistry. And it turned out that there's quite a lot of it. So here's data from Phil Stevens' group at Indiana, and you can see the OH radical concentrations. We're getting up into the order of 10 to the 7 molecules per centimeter cubed during these single bleach cleaning events. And then we would see a lot of evidence. We would see rise in the peroxides and the iodide sims. We would see rise in the HO2 radical measurements. And so what this started to raise some really interesting questions about what sort of oxidation was going on. Initially, I thought that it was all happening in the gas phase because I'm used to being a gas phase atmospheric chemist. And so we were thinking about, well, if you have OH, do you also have chlorine atoms? Are you photolyzing hypochlorous acid in the air? And there's certainly a little bit of evidence from some of the hydrocarbon ratios that there's some really interesting VOC oxidation. But it turns out that the light levels indoors are really, really low. So it's very hard to photolyze very much of the precursors. So instead, to start thinking about this, we started thinking a little bit about multiphase chemistry. And so we were able to call up our colleagues at the University of California in Irvine, Manabu Shirawa's group, and talk to them about how to use their multiphase kinetic model to investigate indoor chemistry. So my student, Jimmy Metallo, worked with Pascal Leakey, who is a research scientist in Manabu's group. And she ran this very nice model that considers a huge number of multi-phase chemical reactions, known reaction rates. And then what we did was we constrained the outputs to various measured observations. So if we knew what the concentration of something was, we could tell the model that this is the concentration you're going to have to work with. And then we would model very specific components of the chlorine chemistry. And what was one limitation that turns out to be quite interesting is that we could consider the mopped floor of bleach. So we thought about, well, how thick is that aqueous layer and how fast is it going to dry? But we also wanted to think about the surface chemistry. So we thought about this in terms of the particle surfaces, and that of course tells us something about the wall surfaces as well. So we started thinking about this chemistry, and we were really able to develop a pretty complex or sophisticated model of the multiphase chemistry. And what we found is that we could not explain any of our data without invoking a very substantial amount of multiphase chemistry. So this is multiphase chemistry in the actual bleach solution that was mopped on the floor, as well as chemistry occurring on the indoor surfaces and particles. And so this figure that you have with the chemical mechanisms, we'll dive into detail of a couple of components in a moment, but this shows the overview of what we think was happening inside. So hypochlorous acid is, of course, the key part that you have out of, that you make very rapid in the aqueous solution out of the bleach. And then that hypochlorous acid, that HOCl, can do a few things. So it can volatilize into the air, so hence we observe pretty high HOCl concentrations. It can equilibrate and form Cl2O. It can react with nitrite in the aqueous solution to form ClNO2, which can of course exit the aqueous phase and go into the gas phase. And then what became quite fascinating is that it could interact with ammonia, just ambient ammonia, and form an array of chloramines. But of course, all of the compounds that go into the gas phase can also interact with other surfaces in both on the walls and with particles. So the hypochlorous acid is going to get taken up by those surfaces or particles, and we think that it reacts with NO or nitrate in those surfaces, and we can make HCl, and NO2 can of course react to form Cl2. So molecular chlorine. And then, of course, you can get some photochemistry, even with the very, very small amounts of light. So we managed to, this model managed to really capture the observations very, very well, especially in terms of the timing of multiple species, which on these figures, they look like they're spot on and all rise at exactly the same time. But when you look at the data very carefully, that's not quite right. So you can see different molecules equilibrating between the aqueous phase and the air at different rates. And of course, the model, also we needed to tune the hypochlorous acid uptake rate. And we had to tune that to be quite high And what that really tells us is that there was a lot of uptake and subsequent chemistry of the hypochlorous acid on all of the surfaces inside the home. And so that's not just particle surfaces, that's all the walls and all the tables and any furniture. All of those act as surfaces for chemistry. And we think that there are thin layers, aqueous, mostly aqueous, and some organic layers on all of the surfaces inside a home that enable some of this chemistry. But as I say, these ammonia hypochlorous acid reactions are quite fascinating, because you'll find if you look at a bleach container, it will tell you not to mix your bleach with any ammonia-based cleaners, of course, because that would give you chloramines, which are particularly toxic compounds. And but it turns out that humans just naturally emit ammonia. We also know there's some sources, food sources of proteins or ammonium, but the ammonia is just present inside of a home. What it turns out is that amount of ammonia is sufficient to interact with the hypochlorous acid in the bleach solution. And you form this nice complex equilibria with different chloramines, monochloramine, dichloramine, trichloramine, that NCl3. And they all have health effects at the levels that we observe them. And so what you have in this time series on the top is the concentration in sequential mops of NCl3, so trichloramine in dark purple, and then you see the dichloramine in the teal color. And of course, what you may notice is that the dichloramine shows up after the trichloramine, but the equilibria suggests that the ordering is the other way around. And what's actually happening here is that trichloramine has a very low water solubility. So even though it's not formed as the initial step in equilibrium, it exits the aqueous phase very, very rapidly. But what we see is a consequent uptake of the ammonia concentration. So where ambient ammonia would be about 20 ppb inside the house, we would see that it would drop by about 10 ppb, and then it would take hours to reestablish the gas surface equilibrium in the house. So overall, we could see that the multiphase chemistry really controlled the indoor nitrogen containing species, had a huge influence on those. And just for a matter of context in terms of the NCl3, so we were seeing up to about 2 parts per billion. According to the WHO, levels as low as 20 parts per trillion have been associated with an increase in asthma symptoms. So these are very substantive levels. Okay, other forms of organic nitrogen, one that's quite fascinating to me are the isocyanates. So after we would map the floor, we would see a rise in isocyanic acid, so HNCO, at up to about 0.5 part per billion. But we would also see rises in methyl isocyanate and ethyl isocyanate. And those were impressive to see. These are obviously very toxic, and concentrations on the order of a part per billion are associated with health effects. So we certainly saw relevant concentrations in terms of these isocyanates. In terms of where these methyl and ethyl isocyanates would come from, or even the isocyanic acid, of course, my first thought was, oh, well, this must be indicative of OH or Cl atom-induced oxidation of amines or amides. But it turns out there's also some, again, in order to make the amount and as fast as we observe it, there has to be multi-phase chemistry that's actually inducing those, potentially some of that oxidation. So whether or not that's inside an aqueous layer or on surfaces, we're still working on, but there's some fascinating chemistry there. So whether or not this impacts the aerosol phase, we do see particulate chloride in the aerosol data inside the house. We definitely see a rise after we mop. There's very little secondary organic aerosol, but there's some indication that it is being formed. It's just not a substantial amount. But what's a little more interesting is that we see nucleation of small particles after bleach mopping, but only when you do that on layered days. So only after you have cooked the right kind of meal just in advance. And so we think that there's some VOC linkages to VOCs interacting with the bleach, forming ultrafine particles, so sub-30 nanometer particles. And it turns out that, so John Abbott's group and Chen Wang in particular has done some research showing that you make ultrafine particles when you mix limonene hypochlorous acid in chambers. And so we think that the same chemistry is happening here. So some combination of volatile organic compounds, hypochlorous acid, and maybe the addition of some amines. So are there chemical transformations indoors? Yes, absolutely. Despite the very low indoor oxidant loading, we're not seeing as much gas-phase chemistry, but we're seeing a large amount of multiphase chemistry that's really driven by equilibria and partitioning. All right, so the last couple of notes I just want to put out there is that there's a lovely paper written by Dr. Chen Wang, who's a postdoc with John Abbott's group, and what she seed was more evidence for this multi-phase equilibria. And so she looked at one of these days where we we just had the house, closed it all up, and then we would open all the windows and doors for 10, 15 minutes and then close them and then wait an hour and then go and open them for another 10 or 15 minutes and then close them up for a couple hours. And what you could see is that every time we did one of these enhanced ventilation experiments where we, again, opened up all the doors and windows. So you can see that in gray. The concentrations of almost all of the acids, as well as a lot of VOCs, would go down. And then when we close the house up, we would see this return back to baseline. And so Chen fit those returns to baseline and got time constants for the sort of reestablishment of that equilibria. And those time constants tell you a lot. They tell us that acids tend to equilibrate very quickly, but that you also see different types of organic molecules re-equilibrating at different rates. And so it's evidence that what we think of as volatile organic compounds in the outdoor atmosphere, things like monoterpenes, ethanol, isoprene, even compounds like octanoic acid, these outdoor VOCs behave as semi-volatile compounds indoors, and that's really due to that massive surface area. So that surface area to volume ratio that you see inside the rooms where you're sitting at. Okay, very last note, because I know there are a lot of people at HOMEChem who are thinking about measurements and about instrument development. So Thanksgiving was our example, not only to eat a very tasty meal, but also to investigate a very complex cooking activity and look for the chemistry associated with it. So what we did was we just cooked a massive Thanksgiving meal over the course of a few hours, and then we would eat it, and then we would clean up. And there were a few things that we noticed, but one was a really odd set of NO2 interferences. So we had two NO2 detectors. One was a anode chemiluminescence detector coupled to a blue light converter. So that's the BLC. And then we also had a cavity attenuated phase shift spectroscopy. So one of these CAPS detectors for NO2. And so you can see those histograms here for them in the top figure. So you can see that overall they actually agreed very, very well, except on Thanksgiving. And what would happen on Thanksgiving is that the blue light converter would read extremely negative concentrations of NO2. Hundreds of parts per billion of NO2. And what that tells us is that we had enough photolabile or compounds, organic compounds, that we think we were producing large amounts of HO2 in the blue light converter. And that would react with NO that was there and create products, but that would change the amount of NO plus NO2 that we observed. So we would report a negative amount of NO2. And all of that to say that what this implies is very substantial emission of photolabile VOCs during these pretty extreme cooking events. And so this raises a lot of questions. And one of them is, what's the impact of these very photolabile VOCs on outdoor radical budgets? And I don't have an answer for you because we don't actually know what these compounds are. But there is certainly an interesting question, I think points to the, first off, of course, the power of intercomparisons and multiple measurements of the same compound on any atmospheric chemistry or air chemistry study, but particularly in indoor environments where you're working with extremely large dynamic ranges and concentrations and a lot of complex potential interferences. So in the Thanksgiving experiment, what we saw, aside from a delicious meal, was a huge array of different organic compounds. And we can relate a lot of these different compounds to different pieces of cooking. A lot of the data is derived from time-of-flight mass spectrometry, so we can get elemental composition, but we don't yet necessarily have identities, molecular structures for all of these compounds. But for some of them, you can see that throughout a cooking event, a pretty impressive cooking event, you could get a large number of acids. We could see peroxides. We saw, again, those isocyanates, and then a large number of compounds that we haven't yet identified, but we are sort of working right now to link some of the actual cooking activities and what were specifically added to what we observe in the mass spectrometers. So overall, we saw that VOCs were very high. They behaved like semi-volatile components. We see that multiphase chemistry controls the inorganic chlorine and nitrogen containing compounds. We see secondary production of a potentially toxic array of isocyanates and chloramines, despite running all of these experiments at certainly manufacturer instructions and best practices. Layering activities turns out to matter. So adding VOCs before you cook clean can, of course, change the chemistry. And we see oxidation of VOCs, but we don't see enough yet for substantial indoor SOA formation. So overall, it's a pretty exciting set of data, and really the result of a massive collaborative effort from a huge number of scientists. So with that, I'm going to stop sharing, and thank you for your time, and certainly be happy to take any questions.
Great, thank you, Delphine. Can you hear me?
Yes, absolutely.
Yes. Okay. So everyone, so let's try to coordinate. I guess I'm pretty sure you have some questions. So we can probably use the microphone if you want to, or you can ask the question via the chat, and then we can read it. So do you have any questions?
Hey, Delphine, Eric here.
Hi.
That was really nice talk. Lots of good, interesting data. One quick question I had was I noticed that you didn't talk too much about the OH hydroxyl concentrations. They were, you showed one slide. What were they? I mean, were they pretty low or?
Yeah, so most of the time they were below detection limits, or
Okay.
on the order sort of 10 to the 5 molecules per centimeter cubed. And then when we did certain events, if we cleaned with a large amount of, if we cleaned with pine sol or some terpene-like cleaner, and then opened the windows, then you would make OH from the ozonolysis of those terpenes. So then we would see higher levels. But the bleach cleaning was quite impressive. And I know that Phil Stevens' group is working really hard right now to get a really good box model going to try and explain exactly where all of that OH and HO2 is coming from. And I know it's complicated. But yeah, overall, usually the levels are really, 10 to the 5.
Okay.
Level.
Yeah.
Or lower.
I think Frank has a question in the chat. Can you read it, Delphine, or I can try to read it? I don't know what.
Let's see. So I can read it. So Frank asks, glad you've never used chlorine bleach in your life. Yes, we are too, Frank. So what does this mean for indoor swimming pools? Yeah, so that's interesting. So the only measurements that we could really find, extensive measurements of things like those trichloramines, come from indoor swimming pools. So, and there you can get some pretty high levels of trichloramine, but it hasn't been looked at extensively. But I think there's going to be there has to be formation of those chloramine compounds and all of the other compounds that we see, because of course, again, humans emit amines, and then of course we shed a certain amount of organic compounds and nitrogenated compounds, things with proteins or amino acids in them. So we will see the same chemistry in swimming pools, but the extent to which that happens, I think, is a pretty open question.
Are there more questions?
Hi, Delphine. I have a quick question. I know we're gonna produce chlorine-containing species using bleach and stuff, but I never expected it would be this high. I was wondering, in one slide you showed that when people open windows and doors, you're gonna see a quick decrease. That means the indoor air is just changing with outdoors. I was wondering, have you or has anyone considered the use of bleach or cleaning products, specifically chlorine-containing cleaning products, to the urban air quality or along those lines?
Yeah, so that's a really interesting question, and I have to say, you know, as part of some parts of Asia, I saw that there were certainly cleaning with disinfectants on roads. And it sort of implied that this was bleach solutions that were being applied on roads, and in that case, you're obviously putting a very large amount of chlorine into the urban atmosphere. In terms of individual buildings, it's a little hard to say because there's some of this chemistry is relatively rapid, but it certainly will exit the house through indoor-outdoor air exchange, so what we call infiltration and exfiltration. So that's certainly going to happen. So these compounds will certainly go out into the urban atmosphere. How important they are, I would have said in general, probably not very, because the air will dilute very rapidly in the outdoor system. But in terms of what's going to happen now that more people are using them, I don't know. I think it might not take a lot of addition to change some of the chemistry, certainly on a hyper-local scale. But how important, I don't think anybody's really looked.
So there is another question in the chat.
All right, I see the question is, did you see any carbon tetrachloride? Yes, we did. So we saw evidence for CCl4. We also saw evidence for tetrachloroethene, ethine, which is a rather nasty species as well. So we definitely see those. And the extent to which that comes out of the bleach solution itself, is just sort of cooked in that bottle of bleach versus actually being formed from chemistry, we haven't really been able to tease out. There's sort of some conflicting ideas in the literature about that, but we definitely see some pretty substantial amounts of chlorinated sort of those halocarbons. They were definitely there.
Are there more questions?
Hey, Delphine, it's Jeff here.
Hi, Jeff.
Hey.
Yeah.
So I was sitting here watching it with my stepson, who just graduated from CU as an environmental engineer. And he noticed that he showed the plot of pinene, limonene, and isoprene going into the night. And the isoprene took a definite dip while the pinene stayed constant. Any ideas why that might be?
Yes, good eye. That definitely happened, and the reason for that is that isoprene is a very solid standard human emission. So we breathe it out, and we emit. We definitely emit isoprene as we are all sitting and breathing here, along with a huge number of other compounds, acetaldehyde, ammonia. And so when people left the house, the isoprene source left the house as well. The monoterpenes, there seems to be just enough residual of that inside the, on all of the surfaces inside the house from all of that extensive use. And so we've created this massive reservoir of species, and that was large enough to really see very clearly all the time and at night in that, at least on that one day. So I think that's what's going on. You still have residual isoprene. We also think, of course, building materials matter. So you have to be very careful in extrapolating from our one house to your house or to anyone or to a, standard American home. Which doesn't, is a nice concept, doesn't really exist. But, you do need to be a little bit careful with that extrapolation, especially in terms of concentrations. But yeah, you'll definitely see all of those VOCs in your house.
Awesome, thanks.
Yeah, following on that, like for example, Delphine, like, do you know if there is anything like this, but for other houses around the world? Like, let's say this is for the US, but for Africa or for South America?
Yeah.
You might have different things.
So this level of intense investigation, you know, what we think of as a field measurement campaign in the outdoor atmospheric chemistry world, that has not been done, to the best of our knowledge, at this level in any other houses. But that said, there's been actually quite a lot of intensive measurements. For example, there are several houses that have had a PTR terpenes used to just investigate the chemistry of that one home. And so there have been studies in certainly in California, which is a little bit different from Texas, and then in some places in Europe, there have been some nice measurements of VOCs and HOX radicals and some of those other compounds. So we have a few data points to compare, but they're generally in Western Europe and North America, right? Very specific measurements, and not across the developing world. And I mean, some of the other things that we found through this, I mean, of course, things like furniture really matters. It turns out that siloxanes are a really interesting molecule to think about indoors. It turns out that, you know, you see perfluorinated compounds, you see, you know, brominated compounds. Those are all additives, things that we brought into the homes. And of course, personal care products are another large source of compounds in homes. And those are very, they vary definitely by culture and by region. So we expect very large differences. The microbial environments of homes are also very different on a regional basis. And that's not something I talked about in this discussion, but there were measurements of the microbial communities before, at the beginning of HOMEChem and at the end, and we saw some really interesting shifts there. And those should be quite different in different parts of the world. And so unfortunately, you know, there haven't been measurements in other places at this level, but we're hoping that this spurs some further conversations. And I see the question was asked if we're planning any follow-up measurements, and yes, we are. So we're looking at doing another study, again funded by the Sloan Foundation. World events permitting, it will be next summer. We're looking at doing another experiment along these lines.
Great. One more question or not for Delphine?
I have one quick question, Delphine.
Yeah.
I didn't hear you mention anything about formaldehyde, I don't think.
Yeah.
Did you mention did you measure formaldehyde, and sort of what levels did you see?
We have measurements. There's measurements with a PTR terpenes, and I do not remember off the top of my head what the concentrations were, but they were. I know they were within the realm of what's been observed, but they were sort of on the higher end. There's a prefab home, so that's actually one of the questions that we're planning on addressing next summer, is to get a really targeted high-end measurement of formaldehyde with working with NIST, and that should allow us to think about the different sources. We did a little bit of modeling to think about whether or not some of this oxidation chemistry would produce large amounts of formaldehyde. Limoneno's analysis, of course, is a nice source of formaldehyde, but it turns out, at least our back of the envelope calculations were that was small and not enough to really compete at all with the house material emissions of that compound.
Awesome.
Well, I think it's time to thank Delphine. Thank you, Delphine.
Thank you. Thank you for having me, and I'm happy to take email questions or other discussions.
Dang, that was great. It's amazing.
Great. Thanks.
Good stuff.
Thank you, everyone, for joining.
Thank you.
Thanks for organizing.